Okay, so today I'm hoping that we're going to finish this chapter 8 that we've been looking at identities of trigonometric functions. And so we've been looking at the sum and the difference of trigonometric angles. And now we're going to use that to derive the double angle formula. And so it's pretty easy and not as extensive as some of the other proofs that we were looking at. So let's look at the following. I want to derive what cosine, oops, actually sine is easier. Let's do sine. I'm already having technical difficulties. Come on. So if I want to look at, okay, this happened in college algebra where I wasn't even touching the screen and it was lagging in writing and I had to do a break, but then I figured out, just take out my battery and my pen and I can restart it. Okay, so hopefully that won't work, or that works, yay. I don't know. Okay, so I want to derive the formula for sine of 2 theta. Well, we know what sine of theta plus theta is. So that's identical. Theta plus theta, if I combine those, gives me back sine of 2 theta. So let's rewrite this as a sum of angles for sine. And so sine was sine cosine, same sign, plus sine cosine, or cosine sine, whatever way you wanted to do it. So it was sine of the first, theta, cosine of the second, well, that's theta, same sign plus sine of the second, which is theta, cosine of the first, which is theta. Well, notice those are exactly like terms. Sine theta, cosine theta plus sine theta, cosine theta. There's 2 of them. So if we sum that, that is equal to 2 sine theta, cosine theta. Okay, so we just derived one of our formulas, that sine of 2 theta, a double angle, is equal to 2 sine theta, cosine theta. So sine only has one, cosine special. It can have a couple different forms. We're going to derive it the same exact way. And so cosine of 2 theta, well, we can rewrite this as a sum of 2 angles. So this is the same thing as cosine of theta plus theta. So applying the sum of 2 angles for cosine, well, again, cosine for sum or difference is cosine, cosine, sine, sine, but it's an opposite angle. So this one's going to be in between. So this is cosine theta, cosine of the other one, which is theta. Opposite sign in between, minus, and then sine, sine. So sine of the first angle, theta, sine of the second angle, theta. Well, cosine theta times cosine theta, same angle. So we could rewrite that as cosine squared theta, which is the same thing as cosine theta quantity squared. You just usually write it this way. They're identical. Minus sine squared theta. Okay, so that is one of them. But we can derive the other 3 from this one. And how we're going to derive the other 3 is we're going to use our Pythagorean identity, cosine squared plus sine squared is equal to 1, and of theta. And so let's rewrite cosine. If we know cosine squared, let's just do this. Theta plus sine squared, theta equals 1. let's rewrite what cosine squared theta is in terms of sine squared theta. And we do that a lot, or we were doing that sometimes when we were solving our trigonometric equations. We had to sometimes manipulate it so we had the same trigonometric function in our equation. And so we would use this identity. And so we can subtract sine squared on both sides of theta. So we get cosine squared theta is equal to 1 minus sine squared theta. So if I replace that, then we get this piece right here, 1 minus sine squared theta and then right here is minus a sine squared theta. So let's combine like terms. And so notice you have a negative sine squared theta minus a sine squared theta. So there's 1 minus 2 sine squared theta. Turn this off. And so there's another one of our equations. So again, from the first one, we can derive the third one. But in this time, instead of rewriting cosine squared in terms of sine squared, we're going to use this equation, and we're going to rewrite sine squared in terms of cosine squared. So instead, from this equation, if we had subtracted cosine squared from both sides, we would get sine squared theta is equal to 1 minus cosine squared theta. So let's go back into that first equation that we derived and insert that piece in for sine squared. So here we have our cosine squared theta minus, so this we have to be careful because this is a minus sign in between, and that sine squared theta, when we rewrite it, it's a difference of 2 terms, and that negative is going to have to be distributed to all the terms. So we need parentheses around this, and so this is 1 minus cosine squared theta. And so let's distribute that negative and then combine like terms. So notice we have a positive cosine squared theta minus a 1, and then negative times negative, so this is plus cosine squared theta. So cosine squared theta plus cosine squared theta, that's 2 of them, so that's 2 cosine squared theta minus 1. So cosine was special. It had 3 different forms of the double angle identity, where sine only had 1. So these I typically don't have memorized. I know I can quickly, and faster than I just did it here with you guys, quickly derive them and write them down and have them next to me. Okay, so let's look at why this could be important or where this could be helpful. Let me see if I can pull an example. For some reason. This is saying use half angle. We haven't done half angle. Okay, example. Here we go. So let's say that cosine theta, this is given to equal 3/5. And we're given that theta, this is between 0 and pi halves. So this is telling me that 0 between pi halves, that cosine theta is in quadrant 1. And part A, we want to find out what sine of 2 theta is. So use this information to find sine of 2 theta. Okay, well, let's pull again the formula. Sine of 2 theta that is 2 sine theta cosine theta. We know what cosine theta is. We're given that. And so all we need to figure out is what sine theta is. And guess what we can do?
Make a triangle.
Hey, hope you guys are getting good at those triangles. Yeah. So theta, we know cosine adjacent, which is 3. Hypotenuse is 5. And so we're looking for the opposite sign. So it's the square root of 5 squared minus the leg, which is 3 squared. 25 minus 9 is 16. Square root of 16 is 4. So now we can easily figure out what sine of 2 theta is. So sine of 2 theta, I'm sorry, sine of theta is, well, actually we do want sine of 2 theta. But sine of theta here is opposite, which is 4, over hypotenuse, which is 5. And we know we're in quadrant 1, and so we're okay. And then we know we're given cosine theta was 3/5. So nothing simplifies in the numerator denominator, so just multiply straight across. We have 2 times 4 is 8, 8 times 3 is 24, so we have 24 all over 5 times 5 is 25. So same information, they want you to find cosine of 2 theta. Okay, well, we can use any of the formulas of cosine. So I kind of think of my first one. I think to myself, okay, theta plus theta, cosine is cosine cosine, so that's going to be cosine squared theta, opposite sign minus sine squared theta. So we already know what cosine theta is. We can square it, minus, and we found up here what sine theta was. It was 4/5, and we can square it. So plugging those values in, so we had 3/5 for cosine, and we had 4/5 for sine. So simplify. 3/5 times 3/5 is 9/5. I'm sorry, 9/25. Minus 4/5 times 4/5 is 16/25. So 9 minus 16, that's -7 all over 25. So any ideas why cosine of 2 theta is negative and why sine of 2 theta is positive. So notice here that we were given that theta was in quadrant 1. If we multiplied, and notice this is sine of 2 theta, and this is cosine of 2 theta. If we look at this inequality and we manipulate it to have 2 theta in between those angles, so if we multiplied everything through by 2, we would have 0 is less than 2 theta is less than pi.
Out of the 3 ways to find cosine data or cosine 2 data, how do we choose which one in like certain equations?
So then good question. This one, we would have gotten the same answer, anyone that we would have pulled out and chose.
Mm-hmm.
If I maybe only knew what sine was, or I could have started this one. There is a form where it just has cosine. So I could have done it without using my triangle. So for instance, cosine of 3/5. Let's do it with just the cosine theta angle. Let me just think about it real quick. So this is my cosine. If I manipulated it so it was just cosine, I would replace sine squared with cosine squared, or 1 minus cosine squared. So I can remember, I kind of think of it in my head. And so this is going to equal 2 cosine squared theta minus 1. So this is one of the other forms. And so instead, if I decided to use this form, I wouldn't have had to figure out what sine theta was. And so I could have said, well, then cosine 2 theta is equal to 2. We were given that cosine of theta was 3/5. So if we plugged it in here, squared it, minus 1. So we have 2. This gives me 9/25 minus 1. So 18/25 minus 1. But I need a common denominator in order to do this. Oops. So multiply, common denominator is 25. So notice 18 minus 25, that's -7 all over 25, which is cosine of 2 theta, which we found before with the other formula. And so sometimes using one might just come out faster than one of the other ones. You wouldn't have to do as much work. Sometimes,
Like you're not going to get a different answer with each one?
no, they're identical. And so couldn't be an identity if you got different answers. The other thing is when you're trying to show that an identity is true, or maybe you see some sort of form of this while you're working in an equation, you can change it to any of those 3 forms. And one form might be more helpful than the other. Just like when we were proving identities, going it through it certain ways, we get there the same route, but some ways were a lot faster and easier than others. So for an example, this says establish each identity. So establish.
So Professor, these are called double angles?
Yeah, these are double angles that we just looked at.
Okay.
Which makes sense, right? Because 2 theta is double the angle. So if we want to establish the following identity, let's say you had cosine raised to the 4th power of theta minus sine raised to the 4th power of theta. This is equal to cosine 2 theta. So if I was going to prove this, I could work on either side. I would probably work with my left-hand side, but I noticed that I have cosine 2 theta here. And so we need to start manipulating things and being able to recognize all three of our forms of cosine 2 theta is going to be helpful. And so maybe just writing them on the side. So cosine 2 theta. Okay, so again, cosine of theta plus theta is how I would derive it. And sum of angles is cosine cosine for cosine. So this is cosine squared theta. And then it's opposite sine minus sine sine, so sine squared theta, because they're the same angle. So this is number one. And then I think to myself, okay, if I rewrite cosine squared with 1 minus sine squared, that would give me my second equation, which is 1 minus 2 sine squared theta. And the last one, if I had taken sine squared, replaced it with 1 minus cosine squared, distribute that negative, we would have had 2 cosine squared theta minus 1. Okay, so we can keep that in mind while we're working with the left-hand side. And so again, showing identities, you're only choosing one side to work with and manipulating it to look like the other side. And so working with the left-hand side, I notice that I pretty much have a difference of squares here, right? Because this is the same thing. If I want to rewrite this, cosine to the 4th theta, this is the same thing as cosine squared theta squared minus, same thing with the sine to the 4th, same thing as sine squared theta squared. So difference of squares. So this would give me cosine squared theta minus sine squared theta, all times cosine squared theta plus sine squared theta. So notice, again, we have a difference of squares. Do I need that? No, I don't. It's going to fall out right away. Notice that cosine squared plus sine squared. So if you ever see that, you know that should be 1. And notice up here, our first equation is cosine squared theta minus sine squared theta. Notice our first parentheses is cosine squared theta minus sine squared theta. And so this is just equal to that because it's times 1. Okay. Which equals cosine 2 theta. Okay, so like I said, being able to identify and see all those 3 formulas, knowing them or writing them down is helpful because you might have to use one of those formulas to help you simplify one of your identities to prove it.
So, Professor, so you're choosing one side to work on to make it look like the other side?
Exactly. So if it ever says establish an identity or prove an identity, you're only working on one side. If it says solve the following, that's where you're trying to get the variable or angle by itself.
Okay, thank you.
Yeah. Let me just mute whoever's on. And there's chat, and I just noticed. Yeah, let me mute so I'm gonna mute everybody. And then if you have a question, just come on and let me know. Okay, so let's pull another example, maybe using it with solving equations. Well, if we're solving equations and we have double angles, we have to be careful. And we kind of, I think, looked at some solving equations with not just the argument being a single angle. Let's see. So solve each equation in the following interval. So if we wanted to solve cosine 2 theta, this is equal to 2 minus 2 sine theta. Okay, so different. It's telling me to solve. And it wants only the answers, because there's an infinite number of answers that would work, but they want the only the answers between theta between 0 and 2 pi, including 0, but not 2 pi. Okay, so when solving equations, it's helpful to be able to rewrite our equation all in terms of sine or cosine. Cosine of 2 theta, that was the special one. It had 3 separate ways we could rewrite it. So if I just kind of pull up what we had above and just did, there is one form of cosine of 2 theta that just has sine in it. And so let's rewrite cosine of 2 theta on that one side using that identity. And so using that identity for cosine of 2 theta, we have 1 minus sine 2 sine squared theta, then has to equal 2 minus 2 sine theta. Okay, so we just manipulated our equation just to have sine in it. I look at it to see what type of equation it is. It's quadratic, so that clues me in. I need to get everything to one side of my equation. I tend to prefer a positive coefficient in front of my square term, so let's just add 2 sine squared to both sides. So that would give us a 2 sine squared theta, because there's none over here. And then let's subtract 1 on both sides. So subtracting 1 from this 2 on the other side, so that would be plus 1. And then we still have this minus 2 sine theta. And I'm going to rewrite it in descending order of powers. So minus 2 sine theta plus 1. Excuse me. Okay, so we got everything to one side of our equation. We got it equal to 0. It's a quadratic. See if it's factorable. I do my AC method if my coefficient isn't 1 in front of my x squared term, in this case sine squared term. That's where I look at the coefficient in front of that square times my constant AC. Multiply those together, I get 2. What multiplies to give me that 2 and adds to give me that middle term coefficient b, which is negative 2. Yuck. Did I do that right? Let me just look, because right
what
now.
What does AC stand for?
So basically this right here, I'm kind of going back to factoring when A doesn't equal 1. If A doesn't equal 1, you look at, there's a trick to do this where you multiply the coefficient in front times C. And so in our case, if I looked at this as 2x squared minus 2x plus 1, my A value is 2. My C value, my constant, is 1. So the goal, if your AC method works, is to find 2 numbers that multiply to give you that and add to give you your constant negative 2, which doesn't work. Okay. Let me just, no, just a second. Okay. If it doesn't work, that means we have to go through and we have to use the quadratic formula. So that's where I'm thinking, wow, I'm surprised they would make us do that, but we can do it. Let me just make sure I wrote down the problem right. Cosine 2 theta Yep, 2 minus 2 sine squared theta. Oh, there's my problem. I didn't write down the problem right. It's minus 2 sine squared theta. Okay, so just put a square in that. Put a square right here, minus 2 sine squared theta. Okay, that changes thing a little bit. Sorry. Okay, what's going to happen?
I think the 2 sine squared theta will cancel.
Right. And so we get then 1 is equal to 2. So what does that mean?
Wait, how did you get that?
If I was trying to move the sine squared to the other side, and I added 2 sine squared theta here, and I added 2 sine squared theta here, the sine squared thetas cancel. And so we're only left with 1 equals 2. So what happens when you don't get a true statement back, where all your variables fall away?
Is it no solution?
Right, so there's no solution on this. So this is false. So no solution. Okay, so I knew something was off, or just by it wasn't very clean. Excuse me. Although math isn't very clean a lot of times. And so that's why I wanted to go back and relook at my problem. That one isn't. Let's try another one. What if it was sine of 2 theta? This is equal to cosine of theta. Again, it's asking us to solve, and it again is giving us our bounds between 0 and 2 pi. So solving, it's helpful if you can to manipulate it to be the same trig function. I notice I can't do that. If I look at sine of 2 theta, so let's just recall what that was. So sine of 2 theta. So think in your head, theta plus theta. So sine of a sum is sine, cosine. So this is sine theta, cosine theta, plus sine theta, cosine theta, same sign. So there's 2 of them. So we could rewrite this left-hand side as 2 sine theta, cosine theta is equal to cosine theta. So now we notice this is linear. Well, it was linear up here too. But we also have something in common with both terms. So if we set this equal to 0, we can factor out cosine theta from both of those. And so rewriting it, we have 2 sine theta cosine theta minus cosine theta is equal to 0.
Professor?
Yeah.
I'm sorry, can you screw up a little bit up?
Yeah. Like that?
I mean down.
Other direction?
Yeah. Okay, that's good.
Okay, so factor out what they have in common. Notice I have a cosine theta in common. We manipulated it to be that way. So pulling that out, we have cosine theta times the quantity 2 sine theta minus 1 equals 0. So now that it's in factored form, set equal to 0, we can set each factor equal to 0. And so we're looking at when is cosine theta equal to 0? And when is the factor 2 sine theta minus 1 equal to 0? So we could take the cosine inverse of both sides of this equation. This is where I didn't start with an equation with my inverse functions. And so this is where when you use inverse functions in your equation to solve, we don't have to worry about limiting those domain. We have to look at all those values of theta that would give me back 0. Well, there's only one between 0 and 2 pi, and not including 2 pi. I just kind of think backwards because that's how I do it when I look at cosine inverse. So what angle gives me back 0 for cosine? Actually, there's multiple values. Well, cosine is your x value. X is 0 here and here. And so x is 0 at pi halves. And at 3 pi halves. So solve our second equation, isolate sine theta. So if we add 1 to both sides and then divide by 2, so we get sine theta then is equal to 1/2. So sine is positive in 2 quadrants. It's positive in the first quadrant and the second quadrant. And so think about what value of theta gives us 1/2 in the first quadrant. So that's 30 degrees or pi 6. So to get that reference angle is pi 6, and it has to be in this second quadrant for sine to be positive. So to get there, we could subtract that from pi. So 6 pi 6 minus 1 pi 6 is 5 pi 6. There's 4 solutions that would make this equation work.
So you're not finding an exact value, you're basically finding the possible solutions to these equations?
Well, they are the exact value of the solutions. So yeah, I'm just trying to find the solutions, the values, the angles that would make this statement a true statement.
Got it, okay.
And they're the only ones, I mean, there's an infinite number of ones that work, but they wanted us to limit it just between 0 and 2 pi. If they had said, find all the solutions, then we have to think about pi halves and 3 pi halves. Well, to get there, if we started at pi halves, right, and we added some value of pi, that would get me to my 3 pi halves. If I add another value pi, that would get me back up to the pi halves, you know, and so adding a multiple of pi would give me that, as long as this was a integer. And then, so that would be this piece. And if I think about it where pi 6 is, pi 6 to pi 6, I probably wouldn't do that. I would do theta is equal to pi 6. But to get to pi 6 again, I would have to add 2 pi k. And then theta to get to 5 pi 6, I'd have to add another 2 pi k. So this would give me all the solutions that would work. And I could find them by like, okay, let k be 2, plug in 2 here, and then simplify. Let k be 0, let k be 1, whatever. I do one more. So this says find the exact value. Of sine of 2 sine inverse of 1/2. Okay, so this is where we're starting with an example, and we have our inverse function in here. So this is where we have to limit what our range is for our inverse. So inverse for sine inverse, the range is between negative pi halves and pi halves. And so the value that would give me sine inverse of 1/2, well, 1/2 sine of 1/2 is 30 degrees, so that's pi 6. So this is right here is just pi 6. So let's just rewrite it. So we have 2, no we don't, we have sine 2. And then that sine inverse of 1/2, this was pi 6. So let's simplify the argument. I mean, we can simplify it because I know that we know what those values are, because this reduces to a pi thirds. If I didn't know it, I could rewrite it maybe as my because I know pi 6, I could rewrite it as with that double angle. But this works. This is 2 times pi 6. Well, 2 goes to there. This is pi thirds. So sine of pi thirds, sine of 60 degrees is root 3 over 2. Okay, so half angle, let me just do it real quick.
Can you scroll down a little?
Yeah.
Down. Sorry.
So while you guys are copying that down, let me pull this other formula. Okay. I've always gotten to the point where this part of the semester, I am like trying to go a lot faster. And so I stopped proving these identities. And so I haven't gotten to prove this one for a while, but it actually isn't too bad. So proving our half angle identities. So we want to find like cosine of theta over 2. And we want to figure out what the formula is for sine of theta over 2. So we're going to rewrite cosine of 2 theta We're going to rewrite this in terms of one of our identities. And let's rewrite it. One, we're going to use both of two of them. So for one, we're going to use it with the cosine squared theta. And that one was 2 cosine squared theta minus 1 was one of the formulas. So here, let's isolate cosine squared theta. So if I added 1 to both sides, we get cosine of 2 theta is equal to, add 1, so plus 1, is equal to 2 cosine squared theta. Let's divide both sides by 2. And so we get cosine squared theta is equal to cosine of 2 theta plus 1 all over 2. If we take the square root of both sides, we get cosine of theta is equal to plus or minus the square root. I'm just going to rewrite this just because this is how you'll see the formula with a 1 first, but the sum of those two terms, it doesn't matter order. So this is the same thing as 1 plus cosine of 2 theta all over 2. So this plus or minus, well, actually, before we do that, let theta equal a divided by 2. So let's just go back in. Wherever we see a theta, we're going to go back and we're going to replace it with a over 2. So if we do that, we have cosine of a over 2 is equal to plus or minus the square root of 1 plus cosine of 2. We see theta there, replace it with a over 2 all over 2. But notice that this 2 times a over 2, both are in the argument, so we can simplify. Those 2's cancel. So here is our half angle formula for cosine. Cosine of a over 2 is equal to plus or minus the square root of 1 plus cosine of a all over 2. This plus or minus depends on the quadrant that you're following in. Okay, so same sort of idea to figure out what the half angle is for sine. So we would start with sine of 2 theta. Actually, we're going to start with, again, with cosine of 2 theta. So using, again, one of the identities for cosine, cosine of 2 theta, this is equal to, but I'm going to rewrite this one in terms of just sine. And so that one was, sorry, let me think. Come back up here. Cosine, cosine, sine, sine. So that's 2. That's 1 minus 2 sine squared theta. Okay, so in this case, let's solve for sine.
This is a different problem from the one before, right?
So we're just deriving, yeah. So both of this problem, we want to derive both of these formulas. So we just derived this formula, and now I'm trying to get this one.
Oh, okay.
And this one, again, we'll use it by using one of the double angles for cosine is how you can get it.
And Professor, these are half angle formulas?
Yeah. So this is that half angle formula right here for cosine. And so we can get the half angle formula for sine if we now look at this identity for cosine of 2 theta and solve for sine theta. So we can do that by subtracting 1 on both sides. So we have cosine of 2 theta minus 1 equals negative 2 sine squared theta. If we divide everything through by a negative 2, that's the same thing. Well, I don't like the negative down in my numerator. I can pull it out front and I can actually distribute it to my numerator instead. Sorry, negative in the denominator. So if I do that, that's identical to 1 minus cosine of 2 theta all over positive 2 equals sine squared theta. So I just pulled this out front just so you guys know, and then we distributed it. And then take the square root of both sides. That would undo my square. So sine theta is equal to plus or minus the square root of 1 minus cosine 2 theta all over 2. Again, if we let theta equal a over 2, we can go in there and plug that in for theta. So that would give me sine of a over 2 equals plus or minus the square root of 1 minus cosine. But when you plug in a over 2 and it's multiplied by 2, that's just going to give you a all over 2. So they're almost identical, the half angle. One just has a plus in between and one has a minus in between. And again, the plus or minus depends on quadrant. So let's pull an example real quick. So it says, use the half angle formula to find the exact value of each expression. So we have cosine of 200, not 200, we have cosine of 22.5 degrees. So we can do this without a calculator. We're going to manipulate this 22.5 to look like something that we know. we're trying to look for the numerator. We're trying to get a 2 in the denominator, and for something that the numerator we know how to evaluate. Well, with these half angle identities, let's multiply this by a fancy 1. Let's multiply this by 2 over 2 for our argument. So if I do that, this gives me cosine 22.5 times 2, that's 45 degrees.
Excuse me, Professor?
All over 2, yeah.
How did you know to put 2 in for A?
Right here? Or where are you looking at?
Where it says cosine 22.5 degrees times 2 over 2.
Okay, because it told me I'm going to use the half angle identity. And in order to get a half angle identity, it has to look like something divided by 2. And so I can manipulate this 22.5 to be over 2 or to be equivalent by multiplying by a fancy 1, 2 over 2. So that would get me, 2 in the denominator, which I need in order to use this half angle identity. Plus it makes my numerator an angle I know.
Okay.
And so here, think about if you're going to have a positive or a negative. Well, our angle, right? We're given our angle. This angle here is in quadrant 1. So I know that my result is positive when I'm looking at plus or minus. I'm looking at the wrong one. So the formula says for half angle, the square root, it's always 1, and it's always something cosine of the numerator. Cosine, I remember it's plus because it's cosine in here. Sine, I remember it's minus because it's not the same. I don't know. That just works for me. So all over 2. So I just applied this half angle formula, and now we can simplify it. So this gives me 1 plus cosine of 45 is root 2 over 2, all over 2. My numerator, this is getting a common denominator. This is 2 over 2 plus root 2 over 2. So that numerator could be rewritten as root 2 plus root 2. Come on. Okay, so 2 plus root 2 all over 2. That was just getting a common denominator in this numerator. And then this is all over 2. So invert multiply. So this is 2 plus root 2 all over 2 times, flip this 2 up, that would be times 1/2. So this is the square root of 2 plus root 2 all over 4. Square root of a fraction is the square root of the numerator all over the square root of the denominator. So we have square root of 2 plus root 2 all over the square root of our denominator, which is just 2. So here's the exact value of this.
In the beginning, why did you do cosine 22.5 over 1 times 2 over 2? What was the deal with that again?
Because it told me I needed to use the half angle identity, so I needed to manipulate this to have a 2 in the denominator.
Okay.
And so the way to manipulate that is to multiply it by a fancy 1.
Oh, okay, got it.
Other questions? Okay, so here's another example. Here's an angle we don't know, but we can use some manipulation. Mm-hmm.
I'm sorry. I got lost, and when you divided everything by 2, the 2 plus root 2 over 2 divided by 2. Why did you divide it by 2?
Part of the formula. The formula is 1 plus cosine of your angle, all divided by 2. And then, so that this piece right here. Are you good with there?
All right, yeah, I forgot.
So I got a common denominator. I just wrote this as 2 over 2. Getting a common denominator, that brought me down, this piece now brought me down to here. And then because I'm divided by 2, I have a complex fraction. A fraction divided by a fraction is really the fraction times the reciprocal of that fraction. So that's where that division comes down to a multiplication problem.
Okay.
And so then that just is multiplying 2 times 2 gives me that 4 here. And then I'm saying, okay, well, the square root of fractions is the square root of the numerator all over the square root of the denominator, but the square root of the denominator, which is 4, the radical can go away and we can rewrite it as 2. Does that make sense?
Yes.
So let's take a break, and then we'll come back and I'll look at maybe 1 or more examples of the half angle, and then hopefully we can get to product to sum to product, or at least start it.
Oh, one more question before we go to break. This was 8.7?
No, this is 8.6. So 8.6 is both double and half angle identities. And so 8.7 would be product to sum to product. And so, but I want to do at least 1 more half angle from this chapter or section.
Okay, all right, got it.
Okay, so let's meet back at 11:40. That gives you 15 minutes. Okay. Let me pause. So this next example asks us to use the half angle formula to get the exact value. But this is an example that we could actually use a sum or difference of 2 angles to also get the exact value. So this asks us to evaluate sine of 195 degrees. And it told us to use the half angle. Identity. Okay, so I basically need to manipulate this 195 degrees to be a half angle. And so I need a 2 in the denominator. And so I can manipulate that by multiplying 195 degrees by a fancy 1 of 2 over 2. And that would get a 2 in the denominator, which I want. So if we multiply 195 by 2, that gives me 10. 2 times 9 is 18 plus 1 is 9. 19, that's 390 degrees. So now it's a half angle. And so we can use our half angle formula. And so it's plus or minus. Well, let's look at where 195 degrees is. If we look at 195 degrees, well, that's 180 degrees, so that's our x-axis, plus some 15, not very far, but it's in our quadrant 3. sine is negative in quadrant 3. So we're going to use the minus sign with this. And then it's the square root of 1. This one is a sine, so we're going to use minus. And then it's cosine of our numerator, 390 degrees, all over 2. So let's think about 390 degrees. Well, that's 360 degrees, which is a full circle, plus 30 more. So 390 degrees is equivalent to 30 degrees. So reference angle is 30 degrees. So we can evaluate this at negative the square root of 1 minus cosine of 30 degrees all over 2. So this is equal to negative square root 1 minus, well, cosine of 30 degrees, that's root 3 over 2. And then we have that whole thing divided by 2, where everything is under the radical. So we're going to manipulate this and clean it up because we have a complex fraction. I guess one way we can think of this, this is probably faster. Let's cancel that complex fraction, this fraction within the fraction, by, again, multiplying by a fancy 1. So if we do that, instead of getting a common denominator and then invert multiplying, this is so much faster. This is equal to negative square root. Well, 2 times this 1 up here is 2. The whole point of doing this was so that our fraction would go away. So that gives us minus root 3 all over our denominator. 2 times 2 is 4. But this is the same thing as the square root of the numerator. So negative 2 minus root 3 all over the square root of the denominator, but the square root of 4 is 2. So sine of 195 degrees, the exact answer is this. Okay, so I want you to do the same thing, find the exact value of sine of 195 using either the sum or difference. Or difference of angles. Because this is where we kind of have to manipulate 195 to be 2 angles that we know. And so just kind of play with it. So let's just come down here and play with it. So we know an angle 30 degrees. And so if we subtract 30 degrees from here, that would give me 165 degrees. So I kind of think to myself, is that one I know? If I do 165 degrees, I would need 15 more degrees to get up to 180, and I don't know 15. I could use a half angle identity on 15, but I don't want to do that. And a sum and difference, so that one doesn't work. So I would go to 45 if I'm doing subtraction. I guess I can do addition too. So let's see, 195 minus 45. Let's see what answer we get back. And so this is 50 degrees. 150 degrees, we know that one. That's over here, 150 degrees, and we need 30 degrees to get to 180, a reference angle of 30 degrees. So if we rewrite 195 degrees this is the same thing as sine of the sum of 150 plus 45. And so now we can use the sum of two angles for sine. Both of those we know. So sine, the formula for the sum of angles is sine cosine, same sign plus sine cosine. So sine of the first, 150. Cosine of the second, 45. Same sign plus sine of the second, 45. Cosine of the first, 150. So 150 is contained in quadrant 2, and our reference angle is 30 degrees. So I think of myself sine of 30 degrees. That one is the 1/2. Sine in quadrant 2 though, y in quadrant 2 is positive. All times sine of 45 degrees, which is root 2 over 2. We're in quadrant 1, so it's positive. Plus sine of 45, again, we're in quadrant 1, so we're positive, root 2 over 2. Cosine though of 150. That's 30 degrees. Cosine of 30 degrees is root 3 over 2. But cosine in this second quadrant, our x value is negative. So this is negative root 3 over 2. So if I multiply out my denominators, 2 times 2 is 4 here, 2 times 2 is 4 here. I notice I have a common denominator, so let's just put it all over 4. So my numerator for the first multiple fractions, 1 times root 2 is root 2. And then over here, I have root 2 times a negative root 3. So it's going to be a minus. And I can multiply underneath the radicals if they're both positive numbers under there, and they're the same index. And they are, so this is root 6. So another way to do it and getting the exact value, sine of 195 by the sum of two angles gives us root 2 minus root 6 over 4. If you scroll up here, notice this is a little different. If you evaluated that and you plugged in those values into your calculator, you'll notice that these results are actually the same. Okay, so I just want to kind of tie it together that there's multiple ways that you can do this and manipulate some angle that we do not know into angles that we do know and use the formulas to evaluate and get an exact answer without a calculator. We could have rewritten this. I also noticed this could have been a difference of two angles. If you wanted to start thinking about differences, start adding angles that you know to the angle that you're given. So I know angle of 30 degrees, right? And so if I added 30 degrees here instead of subtracted, this would have given me 225 degrees. And I think to myself, well, 180 plus 45 is 225. And I know 45 degrees. So this would have also worked. I could have said, well, sine of 195 degrees. This is the same thing as sine of 225 degrees minus 45 degrees. Oops, not minus 45, minus 30. Okay, so here's another way we could have evaluated this with angles that we know, but I'm not going to do that because I don't have time. Where are we at? There's a couple of more examples I was going to look at, but I'm going to jump and just go into the product and sum to product of angles. And that's the last section, and it's not as extensive as the other ones have been. So let me do that. I'm going to change the page. We have a sum to difference. Oops. Where did it go? Product to sum. Here it is. Okay, I'm going to start this a little differently, and I'm actually going to give you the formulas first, and then we're going to drive at least two of them or one of them. I don't know. So theorem for product to sum. Okay, so if you have a product of two trigonometric functions, sine of alpha times sine of beta, this is equal to 1/2 times the whole quantity, so put brackets, cosine, the argument is alpha minus beta, minus cosine of alpha plus beta. The other one is if it's a product of two cosines. So if we have a cosine of alpha times some cosine of beta, this is equal to 1/2 all times the quantity cosine of alpha minus beta plus cosine of alpha plus beta. And then if we have a combo, if we have sine of alpha times a cosine of beta, this is 1/2 times sine of alpha plus beta plus sine of alpha minus beta. Okay, so notice that we have two formulas here. We are looking here at cosine of alpha minus beta, and we have a cosine of alpha plus beta on this other side. So let's first rewrite out both of these formulas we know side by, or one on top of the other. And so we know here that cosine of alpha minus beta, so a difference of two angles for cosine. So remember that's cosine, cosine, sine, sine. So this would be cosine of alpha, cosine of beta, sine, sine. And it's opposite sign, so plus sine alpha, sine beta. And then we also have cosine of alpha plus beta. Okay, sum of angles for cosine again are cosine, cosine, sine, sine, opposite sign in between. So cosine alpha, cosine beta, but this time it's minus sine alpha, sine beta. So to derive one of the formulas up here, you're going to sum both of those formulas together. And to derive another one, you're going to subtract. So derive one by adding. Both equations together. Oops. And the other, or another. By subtracting. Okay, so let's look at it. If we summed both of these equations together, so if I'm summing this left-hand side of both of these equations together, I would get cosine of alpha minus beta plus cosine of alpha plus beta. This is equal to, well, summing both of these together, I'm going to just put a plus up here for now. Well, cosine alpha beta plus cosine alpha beta, those are identical, they're like terms. So this is going to give us 2 cosine alpha cosine beta. And then sine alpha beta minus sine alpha beta, well, those cancel each other out. And so we don't have anything. So notice we're almost there. This multiple of 2 cosines is the sum of those 2. But there's a half in front, so we could just divide both sides by 2. Sometimes it's helpful to notice this formula, use this. But if we divide both sides now by 2, or we can think of it as, how about this instead? Multiply both sides by a half, the reciprocal, because this had a half here. So we got one of them. We know that the product of cosine of an angle alpha times cosine of an angle beta is going to equal 1/2 of summing cosine of alpha minus beta plus cosine of alpha plus beta. Okay, so the other one, okay, so this is the one with the addition. If we did subtraction, so let's go back up to those 2 equations again, and let's do subtraction between the 2. And so if we do subtraction between the 2, we got to be a little bit careful. We had this cosine of alpha minus beta minus cosine of cosine of alpha plus beta. When we subtract, though, we have the first grouping, or we have the cosine of alpha minus beta. I'm gonna need a lot more room. I'm gonna flip it the other way. I'm gonna need the cosine of alpha minus beta, which is cosine alpha, cosine beta, opposite sign plus sine alpha, sine beta. But it's minus the whole quantity of cosine of alpha plus beta. And cosine of alpha plus beta, well, cosine again is cosine, cosine, so cosine alpha, cosine beta. And then it's opposite sign, so minus sine alpha, sine beta. So distributing, we would get a cosine alpha, cosine beta. The other like term here is negative cosine alpha, cosine beta. So those cancel. Oops. And then sine alpha, sine beta. But then we also have a plus sine alpha, sine beta. So here we get a 2 cosine. No, it's 2 sine alpha, sine beta. Let me just bring that piece down. So now if we multiply both sides by 1/2, we have the product of two sine functions. So sine of alpha, sine of beta is equal to 1/2 times the quantity of cosine of alpha minus beta minus cosine of alpha plus beta.
Professor, I had a quick question.
Yeah.
It's regarding the fact of when you need to know, or how do you determine when the equation that we use for either cosine or sine for alpha plus beta is going to be negative. I don't know if I'm stating it correctly.
In here, it doesn't matter if we were given an angle that was negative because it's cosine or sine, we can use the fact that it's an even or odd function to change it to the positive of that angle is what I would do. I think if I'm answering your question, right?
Yeah, I'm not saying it correctly, but what I'm saying is for a sum and difference identity, how do we know which identity to use if we're trying to find an exact value, like let's say of cosine of 165? Like I have them separated for
Okay.
like I'm just like working on a separate problem as well as listening.
Okay, so it wouldn't be using what we are doing right now. So if you had cosine of 165, because that's not a product, right? Or a sum of two angles. But if I wanted to manipulate this one, so this is kind of going back to either a sum or you want a sum or a difference?
Yeah, I'm just trying to find the exact value, and I have cosine of 45 and cosine of 120. And it changes those into radians.
Okay.
But how do I determine if it's a sum or a difference? Like which one do I use if I'm just trying to find the exact value?
It doesn't matter. Choose either one. So just kind of start manipulating it. So if you find it's the sum, like you said, with 120 plus 45, that works. But we probably could have manipulated this too by maybe adding, let's see, if we had added 45 degrees to this, this gives me 210 degrees, right? And I noticed that I also know what 210 degrees is because that's 180 plus 30. So I could have rewritten this 165 also as cosine of 210 degrees minus 45 degrees.
Oh, okay.
So you just have to, and it doesn't matter which ones you choose, but you want to choose something, the two angles that you know when you either sum them or subtract them, that would get back to the one that we started with.
Gotcha. So it can either be over, but you subtract it. Okay, and then there for adding both of them to get 165. Got it.
Yeah.
Thank you.
Yeah, no problems. Any other questions? And so I think that 165 too, we probably could have done as a half angle. Let me just see. 165 times 2. That's 10, 12, 1. It's 330. Yeah, so we could have even done this as a half angle because 330 degrees is an angle that we know. And so I could have rewritten this as cosine of 165 degrees times 2 over 2, which is cosine of 330 degrees over 2. And so now it's in the form that I know how to evaluate cosine of my numerator, and so I can use my half angle. So when I put it in that form versus the other ones, it might look a little differently, but if you evaluate it in the calculator, or if you did some manipulation, you'd get the same, you'd show that they're the same. Let me just do one of these. And so if we have cosine, let's say, of 285 degrees times cosine of 195 degrees. So if you go back to our formula to cosine, this was equal to 1/2. Well, we summed the difference. So this was alpha, cosine of alpha minus beta. And then it was plus cosine of alpha plus beta. So if I knew how to evaluate these angles, I wouldn't be going through all this mess. And so I'm hoping that this is going to help me. And so this is equal to, and I notice in here my alpha value is 285 degrees. And my angle beta, this is equal to, in my problem, 195 degrees. So let's just go back and plug those values in for alpha and beta into the formula. So we have cosine. Well, alpha minus beta, that's 285 minus 195. And so that's 90 degrees. Actually, let's just put it there, 285 minus 195. I'm going to put below, that's 1/2 times cosine of 90 degrees. And then the other piece was plus cosine of alpha plus beta. So that's 285 plus 195. So plus cosine, well, summing those, okay, that's 10, carry a 1, that's 10, 18, carry a 1, that's 480 degrees. If I did that right. Okay, 480 degrees, I need to look at where that is. So looking at my triangle or my unit circle, I know I have to go 360. And then 360 plus 90, that is, sorry, that's 450, right? 450 plus 30, that would get me right here. That would tell me my reference angle is 60 degrees. But in quadrant 2, and cosine is negative in quadrant 2. Okay, so we have, this is equal to 1/2 cosine of 90 degrees. It's on the positive y-axis. Cosine is your x value, and that's 0. This is going to be minus, because cosine is negative in quadrant 2, and cosine of 60 degrees is 1/2. So this is really 1/2 times negative 1/2, which is negative 1/4. So if it says express three theta times sine, oh, sorry, that's sine of 3 theta. times sine of 5 theta especially each product as a sum containing only sines or only cosines as a sum of only sines or cosines. Okay, so notice this is a product. Product for sine, that's where we did the difference of the two. So let me just rewrite what it was, sine of alpha, sine of beta. This was equal to 1/2. And we had found the difference of cosine of alpha minus beta minus cosine of alpha plus beta. Let me just make sure. Yep. Okay. And so notice here that our alpha is 3 theta and cosine, or I'm sorry, beta is equal to 5 theta. So plugging those in, we get 1/2 cosine. Well, 3 theta minus 5 theta, this is -2 theta, minus cosine alpha plus beta. 3 theta plus 5 theta, that's 8 theta. Okay, negative cosine is an even function, and so this is the same thing as cosine of 2 theta. And this is minus sine of 8 theta.
Why is it sine?
I'm not sine. I don't know why I said sine. It's cosine.
Okay.
Just to make sure you're listening. No, that's not true. I wish it was true. Okay. I believe we're done. I don't have the answer right here though. I don't think we need to manipulate that, but if they wanted this as a single angle, then we definitely do. So let me just see if that's how far they want us to take it. Eight, 7. Number 10. Yeah, we're done. 1/2 cosine of 2 theta minus cosine of 8 theta. I didn't know if we needed to break this down as a single angle, and then we would have had to do some manipulation with identities. Okay, so that's probably a good place to stop.
Excuse me, Professor?
Mm-hmm.
Was this 8.7?
This is 8.7, so we
Okay.
started 8.7 when we came back from break, except for that little side track.
Okay.
No, we did a couple, actually we did a couple examples before we jumped in. But yeah, this product to sum or is 8.7. And so the only thing left in 8.7 is going from sum, going backward, sum to a product. And so we'll look at that tomorrow, and I'm going to jump into 9.5 hopefully also, which is the harmonic functions, which will be a good review of graphing sine functions and cosine functions.